is this little thing here on GeoGebra that I like. That let me type in 3 here. So the whole premise of this is the idea that what I'm showing you is the instantaneous rate of change is this red line. So that's the actual slope of our curve at this yellow dot. And you can see that it's a negative 1/2. Okay. If h is far apart, we see this positive slope. So this very much looks like the graph that I had you drawing yesterday. So this, while it's an approximation, it wouldn't be a particularly good approximation for the slope at this point we're concerned about. But if we make our h a little bit closer, so instead of 3, think of it as a table with a limit. So if I'm going to do that, let's say I just type in a 2 and I hit enter. All right, notice how now these 2 points got a little bit closer together. The distance h has shrunk. Now it's a horizontal line through here, so our slope is 0. If I make it a little smaller still, so now we're going to go to the x value of 1. All right, notice how now as this point gets closer to the point that we're concerned about, it's starting to look more like this tangent line. And again, the tangent line, we know that slope is a negative 0.5. Now our slope is at least a negative number, negative 1/4. If we get closer yet, let me not do 0.1. Watch it change. See how it's getting now closer to the actual tangent line? So as our h is getting smaller and smaller and smaller, we'll do one more here. This is what we tried to draw at the top of the page. Usually I like going to this when it's working, which today it is, because it's much better artwork than what I produce, especially on a computer with a stylus pencil. When we go this close, now look at what our slope is. We're starting to approach a limiting value, and whatever that limiting value is our limit, or is our derivative. All right. So this gives you some numbers. It's a little bit better at understanding everything and seeing it all. So I like showing this when it's working, and today it was working, so we're going to do it while it's still working. So that's what we are essentially doing when we do these problems. We just don't want to have to do a table every time. We can do it numerically, and that's what the graph was ultimately doing with numbers. What we want to do it is algebraically, and then that way we don't have to rely on all these calculations. So for number 7, what I want you to do, you'll certainly have to do this in some capacity on your quiz, is we want to take the derivative of this. So what we talked about yesterday is our new notation for slope is the whole f of x plus h minus f of x over h, and then the h going to a 0. It's really just a formula to allow us to find the derivative of a function. So what we would then do is down here, substitute in what we know for our formula. So here's f of x. So after the minus sign, so if you look up here, after the minus sign is your function. So in this particular problem, our f of x is 3x squared. So we would put that in that location. And then all over h. The other thing that we need is here, we need the f of x plus h. So if I now took this function and I now write it with a composite of x plus h, instead of just having 3x squared, I'm replacing the x with the new composite of x plus h. And that then is what's going to go right here. All right. So we know the formula, the function you're always going to be given, and then we just have to write that function as a composite of x plus h. We're now dealing with a limit problem, which is what we've already quizzed on, what we spent most of our time on before yesterday. So we're going to evaluate this limit. Our first option with the limit we talked about yesterday is just taking this h and substituting it in, and we can't do that because we'll get a 0 in our denominator. So what then that tells us is we go to our next step, which is to simplify somehow. So similar to yesterday, we're going to square the x plus h. So if we go ahead and square x plus h, we would get x plus h quantity squared. Wait, I already have that. Let me actually square this. So x plus h squared would be x squared plus 2xh plus h squared. And then we'd still have the minus 3x squared hanging out at the end. And then all over h. You can see now that 3 can get distributed, so that's your next step. So go ahead and do that. Let's distribute our 3. 3x squared plus 6xh plus 3h squared, and then we still have minus 3x squared all over h. And then we should still have our limit here also. Don't drop that out. That's something that I would be particular about. Okay, we want to keep that in there at all times. Now things like yesterday happen here. We can now simplify this. We're going to see that our 3x squares are going to cancel. So there those go. We would also hopefully notice the two remaining terms. So the 6xh and the 3h squared have a common factor of h. So we're going to pull that out. Do what you want. There's also a common factor of 3. It just doesn't necessarily get us to what we need to do. You'll get the same exact answer. We're just going to pull out the h, however. So pull out the h, and then you're left with a 6x plus a 3h. And then if you remember from yesterday, remember how those then cancel, which is nice. This is still our second step. Simplify and then substitute. So hopefully we now see we can take this h, we can substitute it in for the 3h. And when we do that, what's the only thing we're going to be left with as the h becomes a 0? I throw that out there. It's probably not worth you unmuting. Should get 6x correct. That would be the only thing that we're left with. What that then means is this is equal to, since we started this notation with f of x, we would call this f primed of x. The little tick mark means that is the derivative of whatever the original function was. We talked yesterday, this will give you the slope. So this 6x expression gives us the slope of this curve anywhere we want it. So if we want to know what is the slope at 1, you're going to plug it into that formula. Yeah, David, you got your hand up? Or are you answering, or did you have a question?
Oh, no, I have a question.
Okay, go ahead.
So when finding the derivative, are we not allowed to use the power rule on this?
You are not allowed to use anything but this right now.
Okay.
Because eventually, David, we're going to want to know how to take the derivative of this, how to take the derivative of that. And in order to figure those out, we're going to be using this guy. And then once we know how to do all those, then we'll start doing all of the rules. Okay? So you got to be patient for another week. Okay? All right. So number 8. This one says find the slope of the curve, and then you're given the function, and then you're also given a point. So just recall yesterday, we didn't use the word derivative at all in this problem. You just want to understand when we see the expression or the words slope of the curve, that means derivative. That's what the derivative is giving you, the slope of a curve. So when we read those words put together, it's just saying the same exact thing as number 6 and 7 were. So we know we're going to need for this problem the f of x plus h expression. So we'll get x plus h quantity squared. Actually, go ahead and do that one. It's very, very similar to number 7. I do give you a little extra element here. That point has no bearing on the initial 4 or 5 steps that you're about ready to get started. Do your limit, substitute in the function and then the function with the x plus h, clean it up, simplify it, go through all those steps. It's going to be very similar to number 7. So distribute your 5 after you squared your binomial. Your 5x squareds are going to cancel, so these should have canceled just like they would have in the previous couple of problems. You have a common factor of h. with the two remaining terms. We pull out that h. That's going to allow the h, then cancel the h in your denominator. That's where now we're kind of in business in terms of being able to evaluate this limit. If you're able to get through all that, a lot of algebra here that you just want to be careful of. We hopefully got 10x as our derivative. Okay, we're all agreeing with that. All right, so then from there, what we would write this as, so right now put this as f primed of x is equal to 10x. In the first couple of problems, that was all you were doing. What this stands for, so the tick mark means this is the slope of this function for any x coordinate that we want. What I'm now telling you, I don't want you to give me the derivative at any x coordinate. I want to know the derivative specifically at this point. So what we would now do is write this as f primed of, and then we just look, what is the x coordinate of the point that I'm asking you to evaluate it at? And if we come up here, it's kind of all messy now, but our x coordinate is this -1. So we would write this as f primed of -1. So this will now tell us at the x value of a -1, what's our slope? We plug it into this expression here, and we would end up with a -10. That is specifically the slope at that time, at the x value of a -1. We will eventually get to derivatives. So let's say we have a derivative where, let's say you have a 2x and a y together. Then you would need the -1 and the 5. But since our derivative only is an expression of x, we only need the x coordinate of that point. All right. All right, last one of these. Do the first sentence. So see if we can get through all of this. So the last one of these we're doing today. Find the derivative of that function. So see if we're understanding, where does the formula come from? How are we getting the terms to plug into the formula? Go through those steps to clean it all up and see what we get. One of these days I'm going to get a noise machine, play some Jeopardy music right now as we're sitting here working quietly, break up the silence a little. And then don't worry about the second sentence. You're just doing the first sentence. Find the derivative of that function. Careful with parentheses, brackets, distributing. Here's our formula. Here is the x plus h function. Here is our original function. I just, algebra-wise, squared the binomial, distributed, gives us here. Similar to the previous couple steps, some things should start to cancel. So not only do the 2x squareds cancel like they have been, But if we were thorough with our parentheses and our brackets, the negative ones should all, or the negative ones should also cancel. And what we were then just left with are these two middle terms here, the 4xh plus the 2h squared, and then all over h. If you got like a -2, a lot of times people get a -2, make sure you're putting brackets up here so we know that this negative sign is going to get distributed to both terms when it's more than just a monomial. So next step, pull out the h, and then we're going to be left with a 4x plus 2h all over h. These will cancel, hopefully, okay, crossing fingers here. What we ended up with is a 4x for our derivative. We get through that okay?
Mr. Pinion,
Yeah.
quick question.
Go ahead.
Do we have to include the -1 into the equation if they end up canceling out anyway? Like, can we just include the portion that includes the x?
Do you know they're going to cancel out? Like, what? Like, did you know that was ahead of time?
No.
Yes.
Is it always going to happen like that, or is it just specific to this?
All right. So for this problem, we would definitely want to put that in there because the first time seeing this and the first time doing that, we wouldn't have known that that was going to cancel out. All right. So I would say for right now, you want to put that in there just to make sure that there's nothing tricky that's going to happen. It won't. Like I promise you, it won't happen. But there is going to be a little rule with how we handle the derivative long term because we don't want to have to be doing this all year. We would never finish. We get some shortcuts. And the rule for this does basically tell us that those constants, whatever that constant is at the end, will always just cancel each other out. So we could, now that you've seen these in the future, we could, I wouldn't recommend it. You could just drop those out and not include them in the whole process like you're asking. Okay. All right, so this is our derivative. What I'm now asking you to do, so that's our first sentence. The second sentence is now write the equation of the line tangent to our curve at x equals 2. So there's a lot of lines tangent. I could come over here and draw a line tangent if I wanted. I could draw a line tangent right here if we wanted. What I'm asking you to do is come over here to 2. So 2 would be somewhere over here. So put a dot on 2. And before we write the equation, draw that tangent line in. So draw as best you can a line that would just barely touch our curve and then continue on. So what I'm asking you to now do, write the equation of that tangent line. So this line right here, we're going to write the equation of that line. Done a ton of this in your life. The two things we need to know to write the equation of a line is a point and our slope. We are writing the equation of that red line. So the point, we know the x-coordinate is 2. I'm telling you that. Do it at the x-coordinate of 2 here. So our x-coordinate is 2. Get your y-coordinate real quick. Some people have a brain freeze sometimes with this question. They make it harder than it needs to be. All right, what do we think for our y-coordinates? Good. See Nurayan? Is it Nurayan? Did I say that right? Okay, good. Throwing up 7 fingers. That's good. Here is your function. So you're just plugging a 2 into here. Find f of 2. That'll spit out a 7. So then we have our point. The slope now. Here's what we now need to just understand. The word slope is what our derivative is giving us. That's what derivative means. It's the slope of our curve. We want the derivative specifically at the point 2, 7. If you look at your derivative, our derivative only has the variable x in it. So all we really need to know is the x-coordinate of our point. And the x-coordinate is 2. So here's your derivative. We just want to know when x is 2, what does that give us? And that pretty simply is an 8. All right, 4 times 2. So our final answer, I'm going to write this in red because it's getting all jumbled together. You just write the equation of your line now. So y minus 7 equals 8 times x minus 2. That's the equation of the line that is tangent to our curve over here at the x value of 2. All right. So come quiz time on Tuesday, I will almost certainly make you do one of these. It's probably going to be a question where I do a file upload, and I might want to see your work. You'll take a picture, you'll upload it to either Canvas or Mastery Manager. Make sure when we're doing this limit should be here the whole time. And then just make sure we're showing all this work being thorough with all of this, okay? Definitely be able to do one of those for the quiz next week. All right, so now next page. Yes, that one. All right, so the graph of the function f is shown below. So we just got done doing 3 today. We did 1 yesterday where you were given a function. So in this case, we were given this function up here. And then I asked you to take the derivative of it. We did it algebraically, all right? We had variables, we had numbers, we just kind of went through the formula with our limit. Now we want to do it graphically. The exact same question though. Here's the function, so this guy is our function. What I want you to do over here is graph the derivative of that function. So we're not finding the derivative algebraically, we're going to do the derivative graphically. So go, try that. Oh boy, here we go. Okay, this usually stumps some people the first time you've seen it. I usually see when I walk around the room and kind of look, and people kind of like do these weird little scribbles because they're not real sure exactly what they should be drawing here. So if you're not sure, I promise you, you're not alone in our class of 32, that this would be something a lot of people aren't understanding completely just yet. What this is getting at, and we just mentioned it in the previous couple of problems, is, let's say, for instance, if I ask, hold on a minute, that's why I'm not an English teacher, so don't judge me. If I were to ask you what the definition of derivative is, this is now a fancier word for what word have you been using all year that derivative now means? Anybody?
Slope.
Good, slope. So this is the slope of our curve. Instantaneous rate of change, slope, yeah, Nick, we can combine those two ideas, an instantaneous slope. All right, that's all that the derivative means. So if this is my function, and I want to be producing the derivative, instead of thinking of the word derivative, think of the word slope. So if we go between a -5 and a -2. We obviously have this line segment here. And if I ask you what the slope of that line segment is, nobody would hopefully have a hard time with that. We're going down 1, right 1, down 1, right 1, down 1, right 1. So the fact that my slope is a -1 is just a different way of saying that my derivative value is a -1. They're one and the same. What that means is in the interval of a -5 and a -2. So if I go over from -5 to a -2 within that window, so don't necessarily draw these dotted lines that I'm currently drawing in, but within that domain, -5 to -2, I should always have a derivative value of a -1. So that would look, now let me create less mess. That would mean between a -5 and a -2, we should always have a value of a -1. If you've had physics before, this is something you have probably talked about a little bit, because eventually this won't be f, and f prime is going to become position and velocity. And this is some of the stuff that you've probably done with that. If you understood that one, then we come back over here to this graph. Let me do this one in red so we can differentiate. If I now go from here to here, so from a -2 to 0, notice how this line always has a slope of 2. So in our window from a -2 to 0, so I'm dot this line here, this is our domain, we should always have a derivative value of 2. Okay, following along with all that. Go ahead and do the last 2 segments then, if you haven't done it already. So if you weren't sure initially, hopefully we see these first 2, and now we can go ahead and do the last 2. Terrence, question? Or are you going to give me the answer?
Yeah, I have a question.
Go ahead.
So, did you purposely put open circles on the ends of those?
I did purposely do that. It's not something we've talked about just yet, so I wouldn't worry too much about it. I will say leave those open right now, though. We do want these open.
Okay.
All right. All right. So now, as we continued on, hopefully what we saw is from 0 to 2, the slope of this line is always a -3. So between 0 and 2, we should have a derivative value down here at the -3 all the time. And then the last one, our slope of this little line segment here is a 1. So between 2 and 4, we're going to always have a value of 1. All right, making sense, hopefully. Again, we give it some complicated names, and we'll make it even more complicated eventually, but a lot of this still comes back to the idea of a slope. All right, and then where are we at? 38. Oh, we're good. Your class is good. All right, last page. Number 11. Go ahead and graph y equals x squared on the graph that I gave you. Do it pretty accurately, and by accurately, 0 squared is 0, 1 squared is 1, 2 squared is 4. Don't just sketch it. And then 3 squared is 9. If we go to the other side, -1 squared, -2 squared, and -3 squared. And then as best you can, again, don't judge me. It's not easy to draw on this thing. Draw in that parabola through those points. There. It's actually not bad. Probably done worse in my life. All right, now number 12. I want you to write the equation. So we did something similar with this earlier, of the tangent line to the curve at the point 2, 4. So you're going to get this question all year in varying forms. When we write the equation of a line, you need to know what point do they share. So they always share a point. And what slope do they share? The point is pretty obvious. I just give it to you. It's 2, 4. All right, that's given to you in the setup of the problem. Our slope is our derivative value at 2. Do not redo this whole problem with the long slope formula. This was the derivative we did yesterday in class. If you don't believe me, flip over. We've already done this derivative, and we found this derivative to be 2x. So we're not going to go through all the work already. We already know what it is. So what we want is what's our derivative value at the x coordinate of 2. That's going to be a 4. We can now write the equation of our line. So we'd have y minus 4 equals 4 times x minus a 2. For number 12, that's all you would really need to know. When I ask you to do 13, most of us would probably like to see that in slope-intercept form for the sake of graphing. So let's go ahead and put this in the slope-intercept form. And then this is what we're going to take, and we're going to graph it over here on the right-hand side. So we would have a y-intercept of, make this a little bigger. a y-intercept of a -4, a slope of a +4, so up 4, right 1. And if we do this correctly, so if we did our work correctly, we graph correctly, we should go right through the point 24 and then just basically glance off that point. We're only going to touch it that one time. Go up another 4, 1, and there you go. That's the only point we would be sharing. We should be touching it. Go up 1, 2, 3, 4 again. And then draw that line in. Pretend that's a straight line. But then that's our tangent line to the curve. Next question. So differentiate between 14 and 15. 14 is asking you to find the functional value, so of the function. Here is your function. This is the actual function at 2.1. And then the next question is, using your tangent line, what's the tangent line value at 2.1? So take 2.1. Our function is just x squared. Oh boy, I'm going to do some mental math real quick. So you're going to do 2.1 squared. What's 21 squared? 442? 441? If you have a calculator, somebody confirm that. So I'm pretty sure this is 4.41. Okay, I see a few people shaking their heads, yes. All right, so what this question is now getting at, when we do a tangent line, so if I put a big fat dot on this point here, the point 2, 4 is the only point that is shared between the line and the function. However, if you look at our line and then the curve, make this as thin as possible. On your paper, on my computer, would we agree that it's really kind of hard to differentiate between the line and the curve as long as we stay around this point of tangency? Wouldn't the functional values on the line and the functional values on the curve be very, 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 very similar? Yeah, I mean, they almost look like they overlap. They don't. They only touch each other here at this one point, but it almost looks like they're overlapping. So what a tangent line a lot of times does for us is an approximation tool. So if we didn't know what the function was, we could use our tangent line. So we're tangent at 2. If I just move you over to 2.1, you could hardly tell the difference right here at 2.1. These should be very, very similar values. So if you now use your line, so write the equation of our line from above. So this is our tangent line equation. If I now ask you to find that equation, or that value at 2.1, you'll plug in a 2. Hold on here. You'll plug in 2.1 into that line. And it better be really, really, really close to that 4.41. So this would be 8.4 minus a 4, and what we get for the line is 4.4. So very, very similar, almost indiscernible, the difference in there. One of the things that you will get marked off on, again, I got to figure out how I'm going to be able to do this remotely, but just AP test wise, what you want to understand here, if you give me this answer, you won't get full credit. Whenever we're talking about approximation for some function, what you would have to do is f of 2.1, we need to use the approximation symbol. We want to answer the question. All this right now is the value on the line. What we're trying to figure out is f's approximate value. So by doing f of 2.1 is approximately, and then writing it as 4.4, this here is how you would want to present your answer. It's the approximation for f at the x value of 2.1, and you absolutely must, I would take off a point for this, you must use the approximation symbol. They freak out about stuff like that, and we would just want to get programmed early that if it's an approximation, we need the approximation symbol. All right. All right, then real quick, 16, just make sure we get through all this. Almost the exact same thing. If we're tangent at 2, which we are, and we now just go to 1.9, 1.9 is so close to 2 that the value of the function and the value of the line should be very, very similar. So we're almost doing the same exact thing we just did before with just a different value. So let me make this smaller. So our function was x squared. This I do need help on. I don't know what 19 squared is off the top of my head. What's 1.9 squared? Anybody got that?
3.61.
All right, thank you. So that's our actual value at 1.9. If we now use our line value, should be very, very similar. All right, what is this, 4? Yeah, 4. All right, and that should give us what, 7.6? Yeah, minus a 4. So 3.6, if we were to compare these guys, very, very similar. Here's the exact value of the curve. This is the approximate value on the line, but then just write it as such. The approximate value for my function at 1.9 is approximately 3.6, and that's what we would want to say our answer is. So this is exact. 16 is the exact value. If we weren't able to find that, we can use our line. This would have been our approximate value. All right. Last one, 18, f of negative 3. So if I ask you what is f of negative 3, pretty quickly we would get a 9 there. That one I do know without having to wonder. So f of negative 3 is 9. 19, use your tangent line, approximate the value of f of negative 3. So if we now use our line, what's that, negative 16. Unlike the previous 2 times when we did this, when we did 2.1 and then 2, those were really, really similar values. Right now, here is the functional value at a negative 3. Here's our approximated value at the negative 3. And the question is asking you, why is there such a disparity in values right here? If we go to our graph, anybody want to throw this out there?
One of them is squared and the other one isn't. So it's going to be a positive. It's not going to be.
Okay, good. So the negative is going to square that guy right away. It's going to be positive, and then the line, we're not going to get that sign change. All right, so that's good. That's kind of the algebraic way of doing it. Anybody graphically? Like, what do we?
We're way further away now from like that point where you circled where you said these are all very close to each other.
Good, perfect. So,
way past that.
so we kind of reference where I kind of circled right in here. As long as we stay in this general vicinity of the tangent line, so as long as we stay close to 2, 4, my red line should produce values very, very similar to the actual curve. The further away we get from this, though, the less and less accurate that we are going to become. So way over here at a negative 3, if I extend my line and we look at where our curve is, they're nowhere close to each other. So when we're using these lines for approximations, we need to make sure that we just stay relatively close to the point that we are trying to approximate. And if not, then the error is going to grow pretty quickly. Okay, we finished. Happy about that. Any questions with any of that?
Mr. Kenyon,
Yeah.
when we found like f of negative 3, are we still supposed to use the approximation?
No, because if you're doing the functional value, this is the true value of the function. So we need to use the equal sign. If we're going to use the line to approximate it, the line is the approximation, so that's when we would want to use the approximation symbol.
Okay.
All right. All right, then, real quick, since I have a minute, if on our Canvas page, there's a little review there. I don't rely on this review. Don't think this review is going to get you through the whole quiz. Look over that packet really closely. This quiz usually is a little iffy. I don't exactly know how I'm going to replicate my normal quiz on this chapter, so maybe it won't be as bad this time. I have to figure this out. But make sure you know the packet really well. I do have a little quiz review here if you wanted to try one of those. There's a graph on there. Yeah, and then where are we at here? Yeah, so if you were to look in here, you can print that off, look at it, let me know if you have any questions. You have the calendar There's some questions online or on the book also if you want to look at some and make sure that you can get through those on your own. All right. Okay. If you have a question, feel free to stick around here for the extra 2 minutes. But if you're all set, then we'll see you later. Have a good weekend, and we'll see you guys on Tuesday. All right. All right. Have a good weekend.
Mr. Caney,
Yeah.
is the quiz only on 2.4?
The quiz only on 2. Yes, only on 2.4.
No 2.3?
Correct.
And so why do you say that the quiz review is a little iffy?
No, the quiz itself, sometimes the scores are a little iffy on this one. And I'm saying that don't just rely on the quiz review.